Deep beneath our feet, you guys, our planet is alive. Hidden below the Earth's solid crust lies this entire world of unimaginable heat and pressure, a world that's capable of creating mountains, reshaping whole continents, and honestly, unleashing utter destruction in a matter of seconds. These are volcanoes. They are nature's most powerful windows into the very heart of the Earth. Welcome to this explainer. Today, we aren't just looking at the explosive forces that shape our world. We're going to break down the actual mechanics of how they work, step by step.
So here's our roadmap for today. We'll be covering 1. What is a volcano? 2. The tectonic engine. 3. Magma and eruption styles. 4. Lava and pyroclastic materials. And 5. The types of volcanoes.
All right, let's jump right into Chapter 1. What is a volcano? The anatomy of an eruption.
Okay, so at its core, a volcano is basically an opening in the Earth's crust. Think of it as a giant vent or a chimney that lets molten rock, gases, and ash escape from deep underground. Down at the bottom, you have the magma chamber pooling up and a central conduit that shoots straight up to the vent at the surface. When the pressure builds, that superheated magma, this intense mixture of molten rock and gases from the mantle, rises up. And once it actually erupts out of the crest, that's what we call lava. Oh, and a quick side note, that towering mountain you picture when you think of a volcano, that's not actually the volcano itself. That's just the accumulated cone of erupted material that has piled up over thousands of years.
There's a really great, cheeky question in geology. Can you see any shortcuts? And honestly, volcanoes are exactly that. They're part of a dynamic planet that has been evolving for over 4.5 billion years, and they act as this massive, dramatic shortcut in Earth's continuous rock recycling program. They just bring raw, molten material straight up to the surface, completely bypassing millions of years of gradual change.
Moving right along to Chapter 2, the tectonic engine. We'll look at plate boundaries and hotspots to see where all this magma actually comes from.
So, most volcanoes form near tectonic plate boundaries. This is where massive slabs of the Earth's crust are constantly colliding, separating, or sliding past one another. In subduction zones, for example, a heavy oceanic plate actually sinks beneath another plate. That immense friction and heat cause the sinking rock to melt into magma. And because this newly formed magma is less dense than the cooler rock around it, it naturally starts to rise, fueling these incredibly complex volcanic systems. Every eruption here tells a story written in ash, stone, and fire.
Now, what's super fascinating is that not all magma is created equal. The specific rock that melts dictates the magma's recipe, and this fundamentally changes how a volcano is going to behave. For instance, granitic magma is really heavy on silica, around 70%, and it can contain up to 10% water. Basaltic magma, on the other hand, has way less silica, sitting at about 50%, with very little water, just 1 to 2%. You'll definitely want to keep these numbers in mind, because that silica and water content, it's the secret code that dictates whether a volcano will gently ooze or violently detonate.
But, nature always throws in an exception. Not all volcanoes sit nicely at those plate boundaries. Some form over what we call hotspots. This is where a stationary plume of superheated magma punches right through the moving tectonic plate above it. So, as the Pacific plate slowly drifts, the hotspot itself stays totally fixed. This creates a literal conveyor belt of islands, just like the Hawaiian Ridge, where Kauai is the oldest and Hawaii is the youngest and currently active.
Which brings us to Chapter 3, Magma and Eruption Styles. Let's dig into the physics of the eruption. Here is the million-dollar question in volcanology. A volcanic eruption can release energy equivalent to thousands of nuclear bombs, or it can just be a slow, creeping flow of lava. So why do some explode violently while others just gently ooze? Well, the answer lies entirely in the magma's journey up to the surface.
It turns out there are 3 master switches for any volcanic event. First is buoyancy. Hot, molten rock has a lower density than the cooler rock around it, so it naturally wants to rise. Second is viscosity, which is really just a fancy word for how thick and sticky the magma is, basically how easily it flows. And third is the gas content, primarily water vapor, carbon dioxide, and sulfur.
Let's visualize this for a second. Think of buoyancy kind of like a hot air balloon rising through the cooler atmosphere. But viscosity and gas, think of a shaken soda bottle. If you have highly viscous, sticky magma, like that high silica granitic magma we talked about, and huge amounts of trapped gas, the pressure just builds and builds until, boom, an explosive eruption. But if you have low viscosity runny magma, like the basaltic type, with very little gas, the pressure just fizzles out, resulting in a gentle, effusive lava flow.
Okay, Chapter 4, Lava and Pyroclastic Materials. Basically, what actually gets out of a volcano.
Let's see how those physics shape the lava once it reaches the surface. When effusive, runny magma erupts, it forms different textures depending on how it flows and cools. Lava happens when a high eruption rate causes the top crust to cool super fast, getting violently ripped apart by the molten lava still flowing underneath. This creates a jagged, rough, rubbly surface. Pahoho lava, on the other hand, comes from slower eruption rates, allowing it to form a smooth crust that gets pushed into thick, ropey, undulating plates.
The surrounding environment plays a massive role too. If an eruption happens underwater, the immediate chilling effect forms what we call pillow lava, fat, rounded lumps that literally look like bolster cushions stacked on top of each other. Up on land, if you have cooler, stiffer magma that barely travels far from the vent, it forms blocky lava, which cools into these massive, sharp-edged chunks. But what about those explosive eruptions? That's when you get pyroclastic material. This is the heavy artillery of a volcano. Volcanic blocks are solid, pre-existing chunks of rock larger than 64 millimeters that get violently blown right out of the mountain. Volcanic bombs, however, are actually large blobs of liquid magma ejected into the sky that harden aerodynamically in midair before they even hit the ground. It's wild to think about.
And then we have the finer materials, which honestly are often the most deadly. We've got lapilli, which means little stones in Italian, tiny pebble-sized pieces of magma that harden in the air. But the most destructive by far is volcanic ash. People often think of ash as soft, fluffy smoke. It is absolutely not. Ash is formed when gas bubbles and highly viscous magma rapidly expand and explode, shattering the magma into tiny, razor-sharp slivers of glass and rock. These ash clouds can trigger pyroclastic flows racing down mountains at 700 kilometers per hour, and they can travel across whole continents, disrupting climates and air travel.
Finally, Chapter 5, the types of volcanoes, the forms left behind. All those factors we just talked about, magma type, viscosity, eruption style, they all come together to dictate the final size and shape of a volcano. Basically, basaltic magmas generally result in gentler eruptions, creating vast plateaus or shield volcanoes. But the second you introduce granitic magmas, or a mix of the two, you get highly violent activity, forming towering composite volcanoes or massive cataclysmic calderas.
Visually, the differences are absolutely stark. Take a shield cone, like the ones in Hawaii. They erupt gently and are built purely by fluid lava flows spreading out over great distances, creating a low, rounded profile with incredibly gentle slopes. Contrast that with a composite volcano, or stratovolcano, like Mount Fuji or Mount St. Helens. Those are built from alternating layers of flowing lava and violent pyroclastic ash, resulting in a steep, towering peak that is capable of devastating entire regions.
And let's not forget the cinder cone. They're smaller, usually topping out at around 400 meters, but no less fascinating, with distinctively steep sides. They are built entirely from fragmented pyroclastic material, just accumulated ash and explosively ejected debris that piles up around the central vent over time. And if you see Rocky, the little suitcase-carrying volcano doodle in the notes, it's just a fun reminder that geology doesn't always have to be so serious.
But as we wrap up, we've got to loop right back to where we started. Every towering mountain, every sharp block of lava, and every single grain of volcanic ash carries a piece of our planet's story. It's all just a temporary phase in Earth's living, breathing rock cycle. Igneous rock weathers into sediment, gets buried, turns metamorphic, and eventually melts right back into magma. And remember, despite their destructive force, volcanoes create life. Volcanic soils are among the most fertile on Earth, supporting ecosystems and civilizations for thousands of years.
Scientists are continuously monitoring these fire events using satellites and sensors to better predict future eruptions. From the depths of the mantle to the peaks that touch the clouds, volcanoes are a true testament to the immense power hidden beneath our feet. They destroy, they create, and they shape our world. So, I'll leave you with this. As the rock cycle continues its ancient, relentless loop of creation and destruction, what entirely new landscapes is our Earth preparing to build next? If you enjoyed this journey into the heart of our planet, don't forget to like, subscribe, and join us next time for more incredible stories from the world of science on The Explainer.